How does fusion power work? Nuclear fusion is the engine which powers the stars. Many consider it to be the holy grail of energy technology. A working fusion reactor could supply the world with practically unlimited energy indefinitely, safely and without dangerous or toxic byproducts. Unfortunately for us, that technology is still the stuff of science fiction. Or is it? It lead one reader to ask, what is fusion power and how does it work? Fission and fusion. Before we get into fusion, let's talk a bit about fission. Nuclear fission is the opposite of fusion. It's the process of splitting atoms. When atoms are split, either through radioactive decay radioactivity or through a nuclear chain reaction nuclear bomb, they emit vast amounts of energy and ionizing radiation. Nuclear power plants harness this fission energy to provide electricity to 11% of the world's population. Fusion is the process of combining two or more atoms together to create something new. When this happens with two nuclei with lower masses than that of iron, the process creates a significant amount of energy. When combining nuclei with masses heavier than that of iron, it actually costs energy. The latter is a death sentence for stars. When a star begins to fuse iron in its core, it's about to go supernova. Nuclear fission reactor for now. We're only going to talk about the former, fusing lighter nuclei which can create energy. These lighter nuclei behave in a way that we might find counterintuitive. When we try to push two things together, it takes work and energy to do it. When we try to fuse atoms together, they actually want to stick together once they're close enough. When two atoms stick together and fuse into something new, they release a lot of energy. After the fusion, it actually takes a bit of energy to pull them back apart. Unfortunately, since hydrogen atoms have the same electrical charge, they repel each other when you get them in the vicinity with one another. It's a bit like mini golf. If you're trying to get the ball in a hole on a steep incline, it requires a little bit of work to get it near the hole. But once the ball is over the edge of the hole, it immediately sinks right in and pops into place. It goes home. This is thanks to the strong nuclear force which will keep the atoms stuck together. Larger, heavier atoms work a bit differently. They're barely just holding themselves together and the slightest instability can break off pieces and result in energy being released. This is what we call radioactivity. This effect is what is used to superheat water which can turn turbines and generate electricity for nuclear power plants. 2 ways to fuse. Nuclear fusion research has been ongoing for decades. While progress has been slow, there have been several exciting advancements in recent years. While there are nearly a dozen different methods for achieving nuclear fusion, 2 designs are currently leading the way and have shown the most promise. Those are inertial confinement fusion and magnetic confinement fusion. Inertial confinement fusion. Inertial confinement fusion. A colloquial way to describe inertial confinement fusion would be call it laser fusion. It's an apt description because that's exactly what it is. Dozens upon dozens of the world's most powerful lasers are primed, then shot through the system where they are amplified even more and then focused onto a tiny target. The target is usually a small 10 mg pellet of deuterium tritium. The lasers hit with such force, speed and energy that it compresses the pellet and instantaneously heats up before it has time to fracture or destroy itself through conventional means. This is where the name inertial confinement fusion comes from. The process happens so fast within 10 superscript 1 to 10 seconds that the ions are stuck in place by their own inertia. Once the deuterium tritium pellet reaches a certain pressure and temperature, it achieves ignition. Ignition is the name given the process which the pellet begins a chain reaction causing the contents to begin fusing, thus creating significant amounts of energy. A 10 mg pellet of deuterium achieving fusion is the equivalent of burning an entire barrel of oil. The pellets themselves are a 1-to-1 mix of deuterium and tritium. Both of those are isotopes of hydrogen. The global supply of deuterium is practically limitless. It can be distilled from all forms of water and there are 33 mg of deuterium in every liter of seawater. Tritium, on the other hand, is a bit more elusive. It's a fast-decaying radioelement of hydrogen which is incredibly rare in nature. The total global supply of tritium is around 45 pounds. Fortunately, it can be produced during the fusion process itself. It is bred when neutrons strike the lithium contained in the blanket wall of a fusion reactor. Any future plans for a large, commercial-scale ICF fusion reactor would have to include breeding their own tritium. While experimental laser fusions do achieve ignition, the problem is getting more energy out than you're putting in. The energy requirements for the lasers are quite substantial, and for the U.S. National Ignition Facility NIF in California, they'd need to increase the yield 100-fold just to break even. Another issue is the pellets themselves. If the lasers strike the pellets and they aren't compressed and heated evenly, not only do you run the risk of significantly lowering your energy gain, there's the possibility of not achieving ignition at all. Magnetic confinement fusion. Magnetic confinement fusion is a bit more exotic than laser fusion. The process to achieve fusion uses incredibly strong magnetic fields to squeeze, heat and control superheated plasma. The plasma circulates in a donut-shaped reactor where additional methods of heating the plasma take place. An electrical current is also run through the plasma, and in some cases microwaves, neutral beam injections and radio frequency heating also takes place. The goal is to get the plasma as hot as they can to trigger fusion, with temperatures needing to reach or break 150 million degrees Celsius. Of the two types of fusion systems, magnetic confinement is considered to be the more mature technology and likely the first to achieve a net energy gain. However, it is not without its own challenges. To achieve the required temperatures for self-sustaining fusion, the plasma has to be controlled precisely. That's a huge problem because superheated plasma is incredibly difficult to control. Trying to control it is a lot like holding water in the palm of your hand and then trying to shape it into something. If the water doesn't simply leak out of your hand, it will immediately lose its shape and revert back to a disorganized puddle. Keeping the plasma where you want it, how you want it, and keeping it from touching your walls is one of the biggest challenges facing physicists. Impurities in the plasma and instabilities in the electrical or magnetic currents can also throw a wrench into things and can keep fusion from occurring. There is also the risk of neutron damage to the walls of your fusion reactor. Fusion causes neutrons to bombard the walls and causes the metal to become weakened, brittle and eventually decay. This is good for breeding tritium but not good for the walls of an already delicate system. What's so good about fusion power? As we mentioned at the top of this article, fusion power has the potential to supply us with virtually limitless energy. However, the benefits don't stop there. In addition to energy production, the amount of fuel required to power the reactors is tiny and can be distilled from seawater. Fusion reactors also create less radiation than the natural background radiation we experience simply by living on Earth. Nearly 70% of the world's energy comes from burning coal, oil and natural gas. Since there's no combustion involved with fusion, all that dirty air pollution and waste disappears immediately, virtually overnight. While there is some nuclear waste with fusion reactors, it is negligible compared to the amount of waste a typical fission reactor produces over its lifetime. The waste produced by fusion is also not high-level high-risk and is also not of weapons-grade material. Disposal is much less of a concern since the little radioactive waste produced only remains dangerously radioactive for approximately 50 years. There is also no risk of a meltdown which results in a huge, explosive release of radioactivity, for example Chernobyl. This is because there is no chance of a runaway reaction thanks to the tiny amounts of fuel used. The fuel burns itself up before it can do much else. Another added benefit of fusion power is that it can be used for interstellar space travel. We touch on this a bit here in our previous article. What is the future of space travel? Cold fusion? Cold fusion is a type of nuclear reaction that, hypothetically, would occur near room temperature. Several people over the last few decades have claimed to achieve cold fusion, but thus far, nobody has been able to replicate or reproduce the claimants' results in their own labs with their own equipment. One of the reasons achieving cold fusion is highly unlikely is due to the Coulomb barrier. This barrier is easily overcome at the core of stars and in our experimental fusion reactors due to the intense heat and pressure being applied. Without those extreme environments, sustained nuclear fusion is impossible. In an attempt to get away from the negative stigma of the term, those who continue to research this area of fusion prefer to use the term low-energy nuclear reactions (LENR). Currently, cold fusion is relegated to the same class of science as perpetual motion machines and snake oils. Douglas R. O. Morrison, a physicist working at CERN, has called cold fusion an example of pathological science. The term was coined in 1953 by Irving Langmuir, a Nobel Prize-winning chemist. He used the term to describe an area of research that simply will not go away, long after it was given up on as false by the majority of scientists in the field. He has stated that it is the science of things that aren't so. Thanks for watching. Please subscribe Space Facts channel to see more awesome videos.